Or is that console? Which do you use?
Computer. Make screen bigger.
Main screen turn on.
Teach class for me. Yeah,
How are you, gentlemen?
that could be useful. All right. So let's go ahead and get started. My voice is definitely not very good today. No, but I'm hoping that you guys can still understand what I say.
What?
At least as much as usual. So what we'll do first is to take a look at the homework assignment, and I'll give you guys a few sample programs which I think will be helpful for the homework. But you always have to relate to what we talked about last time, the most general equation of to find the effective address based on the addressing modes. Do you guys still remember that? Sort of? No? Why are you not reading my files?
Files? There were files?
Files that I upload from last week. Let's see, today is the 15th, so this was from the last class. Yep. The recording is started already. Yep, it's recording, and let me make sure it is recording from the right channel. Yep, it's right, recording from the right channel. I don't think I'll ever get the fame or the wealth of Louis Armstrong, because this voice is not going to stick, hopefully.
Wait, what are you talking about, the guy that walked on the moon?
What?
Are they related at least?
Okay, so the one thing you have to remember is this line here. Okay, let me just bump up the font size.
So can you sing us a bar, Dr. Zach?
Can I what?
Sing us a bar.
I can sing What a Wonderful World. My daughter, back when she was in kindergarten, for the Christmas performance, the combined class, the two classes, the four classes, sang that song. That was cute, with little kids, singing that song. Of course, none of them had the scratchy voice, as Louis Armstrong. So anyway, this is the most important part, the effective address of a memory operand. I don't care which one we are talking about. It could be a direct, could be indirect, could be based index, could be based index scaled. Okay, all are variations or specializations of this general form. We have all these terms here. So let me save it for today's class first, and then I will go ahead and make this a little bit more elaborate. Okay, so save as. Stash it into today's folder. So don't forget to download these files that I capture every single class, because I capture it for a reason. Not only for myself to remember what I talked about in the previous class, but also for you guys to download just in case you missed something and could not write down everything that I type on the board. Yep. Sorry?
How can we download it?
How can you download it?
Just know how to download the lecture or video.
You go to Moodle. Okay, I'm hoping that by now people should know this. You go to Moodle, and you go to this class. Other than this YouTube clip here, you will see other interesting stuff, such as a date with files next to it. So those are the files that I capture on that day. I mean, if you see something here, it's probably safe to click it, at least to find out what it is. I typically won't try to post any viruses unless it's brand new and there's no defense against it.
Why would you do that to us?
What if we really love you in class?
And they'll all be recorded. Yes?
Why would you send the viruses that there are no defense to against our lives? What did we all do to deserve that?
Because I want your PC. I want to own your PC. There were some interesting news about the Stuxnet virus. Do you guys know what is the Stuxnet virus? Okay. If you know it, that's good. If you don't know about it, you should know about it. The Stuxnet virus is a virus, but it does not infect a normal computer like your desktop computer. its objective is not to control your PC. It's not to launch DDoS against some banks. It's not to get your personal information or download your tax return or anything like that. Its only purpose in life is to infiltrate a nuclear plant and shut it down. That's the Stuxnet virus. So if you don't know what it is, go to Google and search for STUX, Stux, NET, one word, and just type virus after that, and you will find some interesting information about the Stuxnet virus. It was first discovered by the Iranian who were running the nuclear plant, which was actually not connected to the network at all. And they suspected it got into the nuclear plant by a USB thumb drive or something like that. So that was quite the news, back then, and it still has, generated, several news items. I think the latest one, just so that you guys know, the latest one was related to Anonymous. So you go to Anonymous Stuxnet. Anonymous hackers release Stuxnet worm online. So you might want to, but it's from Fox News, this one. The other one is from the Guardian. Okay, if both Guardian and Fox News say the same thing, it's probably real. So you kind of need a conjunction to merge the two sources into one. So anyhow, that's an interesting one, since we were just talking about viruses. Okay, so getting back to today's note. Okay, this is the one that we want to look at today, or at least at the beginning. D is an expression that must be resolvable by link time. Okay? In other words, for the most part, it is usually resolvable by assemble time, but sometimes you need to wait until link time to resolve it. B is a base register. I is an index register, and S is the scale. The scale can only be 1, 4, 8, 1, 2, 4, 8, 1, 2, 4, or 8. Are there any questions at this point about the general form of a memory operand using the 386 enhanced mode? No questions? Okay. So what if I only give you B? This is also known as which addressing mode? This is just indirect. Okay. What about I give you D and B? This is called based. What if I give you D, B, and I? Based indexed. If I give you B, D, B, I, S, then it's called based scaled indexed. What if I just give you D? Direct. That's it. That is it. In other words, all of these addressing modes are really just different forms of the most general equation. And the most general equation is also known as the based scaled index mode. Do we have any questions at this point? The next question is, what is an effective address? The effective address is nothing more than a bit pattern. In the case of a 32-bit mode, it is a 32-bit bit pattern that becomes the address of where you find the content, where you actually find the actual operand. So that means the address itself is not getting copied. It is the content at the address that is copied. Is that okay? So when you're working with a memory operand, it is not the address that is getting copied, it is the content at the address that is getting copied. Okay, is that okay? Is it helpful so far? Okay. Now, along with this file from the archive from the previous class, there were also sample programs. The base.s, base index.s, these are all programs that we did on the other day. And they're all related to your homework assignment. In other words, if you download this file, run those programs, and be able to explain what the program does, and be able to make changes to the program, predict what the program will do, and verify using GDB, then you should have a better understanding of the material that we have talked about so far. Any questions at this point about a memory operand? Nope. No questions? Okay. So let's go back and take a look at the homework assignment itself and look at the file that I give you. This is the program that I gave you, and there are several places where you can actually change something. I can show you everything that is relevant so far. This is one question mark, this is another question mark, and this is the last question mark. So the question is, what can you do to specify the question marks in order for the program to do what it is supposed to do? What it is supposed to do is to have EDX to have the content of 40002323. That's the question. Okay, basically, it's kind of like an Easter egg hunt, but it is actually easier because there's logic to solving this problem. Whereas in a real Easter egg hunt, there's no logic; it's just luck, right? And talking about luck, when I used to teach the micro mouse class over at UC Davis, occasionally we'll encounter a few mice that we'll call dumb luck mice. In other words, they don't use any AI to search in a particular way, of how to get to the destination. It's all random. So we call those, dumb luck mice. And once in a long while, the officers will not set up a really good maze. In other words, it is possible 1 year a dumb luck mouse actually won the competition, just out of dumb luck. I think there should be a special award for that mouse. Luckiest mouse of the year. So anyway, in this case, we don't need dumb luck to do this. The first thing we need to do is to spell out the memory content. That would be the first step. To spell out the memory content, I'm not going to do this one for you guys, so I will use another example to illustrate what I mean by that. Let's see. So I'll go to today's folder, which means this program will also be saved in today's zip file. At the end of the class, typically somewhere if I have time in the lab, I will upload this folder to Moodle already. So that means for most of you, by the time you get home, you should be able to see this folder. The video clip typically will be uploaded at about the same time, so by 10 o'clock or so, it should be up on YouTube already. Okay, so let's go ahead and write a program to illustrate my point. Okay, I'll just call this mem0.s. And this one is only here to illustrate how do you spell out the memory content. How many people already know how to do this, and I really should not be using the time to do this? No, okay. So in this case, I'll just make it a little bit more interesting. So I would use a dot byte 0x235, and then we have L1, and after that we have dot word. Yep. Larger font. Yes, I can do that. Is that better? Yep. I forgot to make a row sheet. It's mostly because I keep that tune It's a Wonderful World kept replaying in my mind, so I just forgot about the row sheet altogether. Okay, so we have dot word, and then we'll put a dot int. Oh, let's try a 0x235. L205. And then we have L2, yep.
Can we have some ASCII and some ASCIIs as well?
Put some ASCII,
And
sure.
some ASCIIs.
ASCIIs,
Uh-huh.
like that?
Uh-huh.
Sure, okay. Okay. And we'll just call this, dot text, da-da-da-da. I'm not even going to assemble the program because there's no need. Well, I guess I should. Okay, so I'll go ahead and finish the program. So this way I can compare what I think is the memory layout to what it actually is. Because, I can make mistakes. So if I do make mistakes, I want a way to find out, that I made a mistake, and the debugger is the best way to check. Okay, so here we have a useless program. Basically, every time you see the last 3 lines here, these 3 lines, oops. Okay. Line 11 to line 13, they're basically your exit code. Okay, so that's why you see the same 3 lines in every single program, because this is how you ask the operating system to say, okay, this program is ready to terminate. Please take the resources back for other programs. Now, but my main purpose is not to run the program. My main purpose is to spell out the memory content of this entire program. So one way to do this is to use a spreadsheet. You don't have to use a spreadsheet, which is kind of an overkill for something like this. But I will go ahead and use a spreadsheet anyway. Where's my spreadsheet? Office, Calc, there we go. All right,
Can you make the font bigger?
like that.
Oh, nice.
That's big. Okay. Okay, so we want to spell out not only the memory content, but also how the labels relate to the memory content. Okay, because that's what you need to do, is to have a map of everything. Not just what bytes are in memory, not just the order of the bytes, but also which label is the address of which byte. Now remember, the label is only a label of 1 byte. Even though in some of these, let's say L1 colon dot word L2, that's 12, on line 3 and line 4, technically speaking, L2 is the label, L1 is the address of the least significant byte of the dot word construct. It is not the address of the dot word itself. Because remember, the assembler, when you're talking about labels, it has no type. So every address can only be the address of a byte, which is the smallest addressable content in memory. Is that okay so far? Okay, that's a very important concept. It's a big change from C and C++, because when you talk about C and C++, you say int I, and then later on you say %I. %I is the address of I, which is an address of an integer. The compiler understands the type of the address. But in assembly programming, there is no such thing. An address is only an address of a byte all the time. So here we have, I'll just reserve column A for the labels. I will use column B to spell out the content at those locations. So here we have hexadecimal 23, and then we have hexadecimal 05. Now I can just say 5, but it is more clear to say 0x05 because I want to emphasize this is only using up 1 byte. Now, I think from a discussion with some of you, I realized that not everybody understands what is hexadecimal. Base 16. The relationship between base 16 and binary is actually pretty simple. I can use sheet 2 for that purpose. Okay. And let me just magnify this. Okay, we have no problem with the first 10 digits, okay? And then we have A, B, C, D, E, and F in hexadecimal. The question is, what is each one corresponding to in terms of being a binary bit pattern? 0 is 0 regardless. So I'll call this 0T0000. This is a convention of the assembler. When you use the T, it means binary. Or I think, is it 0B or 0T? I think it's 0B. I'll change it to 0B instead. Okay, so this is binary 0000. Well, that's not really interesting, right? 0B 0001, not very interesting. Look at the next one, 0B 0010, right? And so on. Now, when you get to 9, it becomes 0B, it's 1001, because it is 8 plus 1. When we look at binary numbers, the least significant one represents how many 1s we have, and how many 2s we have, how many 4s, and how many 8s. This one has 1 8 and 1 1. 8 plus 1 is 9. Okay. The next one is what we know as 10 in base 10, but in hexadecimal, we borrow a letter from the alphabet. So that becomes 0B 1010, 1011, and so on, and the last one is 0B 1111. I'll leave it up to you guys to fill in the in-betweens, because each one is just adding one to the one before, and even if you don't know how to deal with the binary numbers, your calculator can. Excuse me. So the question now is, why do you think base 16 is special compared to, say, base 10? How do you convert from base 10 to base 2? You have to do a lot of calculations. How do you go from base 2 back to base 10? A lot of calculations. But when you go from base 2 to base 16, it's a table lookup. The table only has 16 items. When you go from base 16 to base 2, it is also a table lookup, the same table. So the only thing you have to do is to see which way you're going. Are you going from base 16 to base 10 to base 2, or from base 2 to base 16? This is also neat because how many bits can we represent using one hexadecimal digit? 4 bits. And how many bits do we have in a byte? We have 8 bytes. So 1 byte can be represented cleanly by using how many hexadecimal digits? That's it. That is why we use hexadecimal numbers all the time. It's because it's very clean. Every 2 hexadecimal digits represent 1 byte. Now, you can think about octal, but octal is not clean because every octal number represents 3 bits. So it's not really, at a byte boundary. But hexadecimal numbers, in terms of the digits, if you go by 2, they always end at a byte boundary. And that's why we like hexadecimal numbers. Is that okay so far?
You say every 2 is
Uh-oh, you're getting my bug. Yep.
you say every 2 hexadecimal digit represent 2 bytes?
1 byte. 1 hexadecimal digit is 4 bits. A byte has 8 bits, and therefore there are 2 hexadecimal digits in 1 byte. Okay. So knowing this part, which is in sheet 2, this is a translation table. We go back to sheet 1, so we keep going like this. The next location has the label L1. The assembler actually associates L1 with this memory location before we even use it. Because when we say L1 colon, it is the same as saying L1 equals dot, which means L1 is a label that is equivalent to the current location of the data section counter, which is the next location to allocate, not the last allocated location. Is that okay so far? So now we stuff it. We just need to put some content into it. Now this has to be, you have to be careful about this one because this is decimal 12. It has no prefix. There's no 0x, there's no 0b, and it does not start with a 0. So it's a regular base 10 number, a base 1012. A base 1012 can be represented by a single hexadecimal digit, which is which one? C. That's right. Okay, but that's only 1 digit. How many digits in hexadecimal do we need for a dot word? We need 4 because it's 2 bytes. So that means we have to pad additional zeros. Okay, let me just show you what I mean by this. I can represent this using just 0C. But as a 16-bit number, it has to be Okay, which end do we pad the zeros? Do we make it 0xC000, or do we make it 0x000C?
000C.
000C is the correct answer. Because if you pad the other way, I want you to work for a bank so that I can come into the bank and have some change. Okay? You can make me rich by being a teller. Okay, so in this case, what I want to represent is 000C. But remember, one row is 1 byte. I cannot represent 16 bits on one single row. So now I have to break it up into 2 rows. The question is, okay, if I have to break it up into 2 rows, which part of this number goes to row 3 and which part of this goes to row 4? Now we need to know which type of processor are we using. Are we using a little endian processor, or are we using a big endian processor? Little endian. So that means, the least significant byte goes first. So in this case, it will be 0C go first, and then 00 goes next. Are we doing okay so far? Okay. The next one is a .int, and this time we have in hexadecimal 205. But remember, this is also misleading because a .int is a 32-bit bit pattern, which means how many hexadecimal digits do I need for a full representation? No, 8. We have 4 bytes, which means we need 4 times 2, which is 8 hexadecimal digits. So we need how many zeros to pad it? We need 5 zeros to pad it. Right? 5 plus 3 is 8. And all those zeros have to be more significant. So that means, when we express this in terms of bytes, it'll be 05 first because that's the least significant byte. Are we doing okay so far? The next one, it will be the next most significant one, will be 02. And then we have 00 and 00. And now we have L2, the definition of L2. After the definition of L2, we have the .ASCII, which is basically an ASCII string but no terminated. So in this case, we have to look up the ASCII code of T, AK, and the exclamation point. And there's a quick way to do it because in Linux, when you type man ASCII, it gives you the ASCII table. So we just have to look up uppercase T. Uppercase T has a hexadecimal representation of 54. So we have 54, and then the next one is lowercase a. Lowercase a is 61. Yep.
Yes, I have a question for L1. You said that we have 4 bytes, so it means we have 8 hexadecimal, right?
8 hexadecimal digits, yes.
Okay. So for L1 we only have 6.
What?
You put L1 equals 0x0c, and then
Yes.
after
These two is one single dot word. And then we have K, which is down here. K is 6B. And then we have the exclamation point. Yep.
Does the little endian argument come into the ASCII Z?
No.
So it's left, right, not like
Correct.
left, left? Okay.
Yep. Whatever is on the leftmost part is the first byte, and then it's just sequential after that. And then the last one is 00 because it is a no terminator. That's the only difference between a .ASCII with an I at the end versus .ASCIIs with a Z at the end. The one with a Z at the end is a no terminated string, which means it can be used in many C functions immediately. Okay, so we have this program here, and this is my representation. That's the data section spelled out in bytes, and with the labels, next to the byte location of that particular address. Now, there are several ways to look at this. Even just looking at this one, there are things that you can do already, because this location can also be known as L2 minus 1. Does it make sense? Well, because we are byte addressing. Each row is 1 byte, so the row before the row that has L2 as a bookmark is L2 minus 1. So So this one is also known as L2 minus 2. This is also known as L2 minus 3. And you just keep up. You can just keep going. L2 minus 4.
Or you do L1 plus 2.
Exactly. They can have aliases. So L1 is also the same as L2 minus 6. They are really exactly the same thing. Okay? So are we doing okay so far with the calculations that we can do with these labels? Each label is nothing more than an integer. You can add stuff to it, you can subtract stuff from it, you can do divisions. Yep.
I tried to do this at home, but I couldn't keep track of the ones that like L1 is dependent upon L2. The one that is like
Okay.
that.
So you're saying something like, okay, let me just change this program a little bit here. So let's say we have L3 here, and L3 is dot int L2. How's that? Okay. Well, that means, we have L3 defined here, right? Because L3 is the label of the byte immediately after the .ASCII construct. What are we defining here? We are defining 4 bytes. So we have, this will be byte 0 of L2. This will be byte 1 of L2, byte 2 of L2, and byte 3 of L2.
And if it was like L4 instead of L2, we go first to L4, and like if we have L3 dependent upon L4, not L2, not something like.
But L3 does
that.
not. Okay, you mean forward referencing?
Yes.
Forward referencing does not matter at all. I can change this program so that it is start. It will work just fine too.
Okay.
Basically what you're doing, you're still reserving 4 bytes. You're still reserving 4 bytes here, except these 4 bytes are no longer 4 bytes of L2, and these will be 4 bytes for .start, underscore start.
Okay.
The assembler can resolve that. So don't worry about referring to a label that is defined later on in the file. That's not a problem for the assembler. Yep.
So if I wanted to, let's say the L3 was pointing to, or it had L2 like you had it before, and I wanted to move L2 into the EAX register, I would send in the first byte, right, byte 0 of L2. That's where I would be pointing to, like originally. I wouldn't go.
I don't understand your question 100%.
Awesome.
Could you say that again? Oh, okay. But are there any questions at this point about how the program is set up right now? Nope. Okay. So I'll just change it back to L2 because whether it's L2 or underscore start, it really is the same mechanism. Are there any questions about this picture, especially these 4 cells? If I want to spell this out even more, yes, go ahead.
So the byte O2 or L2 have the same content as L2.
Well, you have to watch what you're saying because L2 is a label and the label is an address. We don't know exactly what is the address until the program is loaded and ready to run. So all that I can do here is to say this is basically bit 7 to bit 7 of L2. Okay, let me just do that again. Bit 0 to 7.
Why is 0 to 7? Why is 0 to 7?
Bit 0 is the least significant bit, and bit 7 is the 8th bit from the right-hand side. Do we understand the references to byte whatever, bit whatever? Yes or no?
Yes.
Okay. So the next one is the least significant byte, but you can also say it is bit 8 to bit 15 of the 32-bit constant. And then this one is the third one, which is basically from bit 16 all the way up to bit 23. And this is the last one, which is bit 24 to bit 31. So that's the other way to look at it, is to break the 32-bit constant into 4 chunks. One chunk is a bit. Yep.
Is L2 4 bytes?
every address is 4 bytes. Every symbol is 4 bytes. Well, I take it back. The label itself really does not have a width, but when I say .int, then we'll use exactly 32 bits to represent the value of L2.
So if it was .word, you would use like only
If you
byte
use-
0 and byte 1.
Correct. If you use .word, it will do a truncation, which means only the least significant 16 bits will be initialized in memory. Are there any questions at this point about this map here? This is the very first step you have to do to get your homework assignment done, is to identify which label is where and what are the byte patterns in terms of this entire region of memory. Question?
So what if you have .byte, but then you try to initialize it to more than it could hold, say, give it like a more hexadecimal numbers than they could hold, like.
It will the assembler may give you a warning and say that constant requires more than 1 byte. So if it gives you an error, it will stop. It will not give you an object file, and you have to fix it. If it does not give you an error, if it gives you a warning or no warning at all, that means it only is truncating. It's only taking the least significant byte of the constant and leaving the rest basically truncated. Okay. Any other questions about this part here? No questions? Okay. Now, I have already told you guys that you should not trust me, right? So if you don't trust me, then you have to find a way to test it. And we cannot display from L1 because L1 is already 2 bytes past the beginning of the allocation. This location is L1 minus 2. So the next step for us to do is to save the file, assemble the program, mem0.o, mem0.s, ld mem0, mem0.o, there we go, and use GDB to help us. GDB is going to be a very helpful tool. I know it is painful to learn all the commands, but the earlier you learn all the commands, the earlier you can start to benefit from GDB. I can already tell you, we haven't even started to look at, we haven't even started with the full potential of GDB yet at this point. So you really have to get used to GDB at this point so that in the future, next few weeks or so, you will not be slowed down, by, GDB itself. Okay, so here we have our program. I don't even need to run the program. I can actually start to display the content of the program as of now. Now remember the first thing we said? Okay, let's see how many bytes we have to display. We have to display 17 bytes here because I can use the row number in the spreadsheet to tell me exactly how many bytes I have to display. So the first thing I would do is to make a mistake. I would display 17 bytes, each one in hexadecimal, starting at the location of L1 minus 2. This is incorrect.
Because it's an integer point.
Exactly. Okay? This is incorrect, but so where do I learn that this is actually incorrect and how do I fix it? It's already in the links. As I said, most of these links, if not all, should be fairly harmless. So people should be clicking these things already. If you look at AS and GDB, I think it's this one here, it tells you that you have to do typecasting because L1 is misunderstood by the compiler as the address of as an integer, as a global static integer. So when you say ampersand L1, the type is an address of an integer. When you take an address of an integer and you subtract 2 from it, the byte location is actually subtracted by 8 because one integer is only 4 bytes. So that's why it's calculated incorrectly. And that's also why you have to do some typecasting before you add or subtract the numbers. So now I switch back to the debugger here. This time I remember, okay, we have to cast it first to a character pointer. Then we can do the subtraction by 2 because one character is exactly 1 byte. And now we have this content here. It's not exactly in the same column format that we have, but you can just do a quick check with our spreadsheet, and you should confirm that they are exactly the same. So let me just do this part here. Okay, so we have 2305 0C 0005 020000. I feel like that I'm spelling out the key of PS3. 5461 6B 2100, and then we have these 4 bytes here. These 4 bytes I cannot put it into the spreadsheet because I don't know exactly what they will be until the program is loaded. So this part depends on a lot of factors. They may not be the same the next time you run exactly the same program. So I would not write your program to only work with one particular instance of the program, because your program has to run correctly when I run it on my computer under the conditions that I'll be running it in. Are there any questions? Yep.
So L3 plus 3 on the side there?
Say it again?
L3 plus 3 over there, is that like address?
Yes. This byte here is exactly this byte here. It's byte 3 of L2, which means it is bit 24 to bit 31 of L2. So if you look at 88, 90, 04, and 08, those 4 bytes spell out exactly L2. Okay? But we can check that. We can double check and verify that just easily. So the first thing we want to do is to ask the debugger, what exactly is the location of L2? Okay, it's this byte pattern, bit pattern here. You can tell right away, okay, because A8 is the least significant byte, 90 is the next significant byte, 04 is the next one, and then we have a single 8 here, which is also 08 here. Is that okay? So I'm hoping that this part here, should be enough to kind of give you guys enough clue of how to get started with the homework assignment. Okay. Now, even though you can do everything just by using the debugger, just like what I just did, it will still be helpful to be able to do it by hand first, okay, and then use the debugger to verify that you did it correctly by hand. Because if you did it by hand and something is not right, it does not match up with the GDB output, then you have to ask yourself, did I make a silly mistake? Did I make a careless mistake somewhere? Just, I forgot, to add 1 more byte to this. Or did I make a conceptual mistake? Because those two are completely different. Silly mistakes, it's okay because the GDB will fix that and will show you the correct answer anyway. But conceptual mistakes can be carried on to the rest of the program and the rest of this class, and that would not be good. So that's why I still encourage everyone to do it by hand first and then use the debugger to verify your understanding of the memory map. Okay, any questions at this point? No questions? So let's go ahead and move on. We are basically all done with operands. So now we are moving on to something slightly more interesting. And let me turn on the editing and remove the link to Louis Armstrong.
It might be important to reference later.
Well, let's hope that I don't need to refer to it later. Let's hope my voice will be okay again soon. Okay, so now we move on to topic number 3. Topic number 3 really doesn't have anything that's really new. We talk about adding numbers. We talk about arithmetic operations. We have done many of these things already. This is a link to the old notes, which I don't really use anymore, but it's not wrong to refer to it. Oh, wait, this is the one. This is the right one. Okay, this is the right one. So never mind what I just said. We talked about adding in binary already. So that's a topic that we have already covered up to this point. Do you guys still remember how to add in base 2? And that was easy, right? No? You guys have been polluted by base 10.
Base 10 is the hard one.
Base 10 is hard. because base 10 has a big, huge multiplication table,
You
and
have
also
to keep
with
track of all those digits. There are like 6 or 7 of them, aren't there?
what
Digits in base 10?
in base 10.
There are a lot. I lost
Yes,
count.
there's a whole bunch of digits. Yes, in binary it's either there or not, so 1 or 0. Okay, so these are the ones that we have talked about already. 0 plus 0 is 0, and so on. The only one that is kind of weird is 0 plus 0 is 0 with a carry of 1. Okay, we talked about this already.
It's 10.
No, it's 1 0. And then we talked about bit operators. Bit operators in this case, this is the conjunction, and that is the disjunction. Okay, basically one is or and the other one is and. Yep.
How do you enter that dot on the keyboard?
Well, this is a typesetting program intended for math dissertations and master's thesis, so that's why I don't have a problem entering that. Okay, but most of the time, if you want multiplication or and, you don't even need a symbol. Okay, in terms of, let me just see if I have more examples later on. So back to adding. Okay, let's take a look at this slide here. This is actually kind of important. This brings us back to the half-adder equations. So let me see if I can find I found a marker, but I think I want to do this using the spreadsheet. Using this slide here. So this is what I would do. Open a new window. And resize it. Okay. And then we go to, let me just kind of go through this slide a little bit. Okay, a single bit is almost the same as a single Boolean. Is that part okay? Because what can you do with a Boolean? What can a Boolean store? True or false, right? What can a bit store? 1 or 0. So if I say 1 is true and 0 is false, don't you think all the operators that you can do with Boolean can also be applied to bits? Okay? So that means when we use conjunction, it is the same as using multiplication. Okay? So when you use conjunction in binary, you can say, x and y using the multiplication symbol. It can be in Boolean logic. Okay, x times y, the symbol times is also used as conjunction. But a lot of times, we don't even simplify, so we don't even use the multiplication operator. Just like in your math class, when you say 5 times x, a lot of times you just write 5x and just not even mention the multiplication symbol. It's exactly the same way here. When you see xy and x is a bit and y is a bit, xy is the conjunction of the two bits, x and y. When we use disjunction, we use the plus symbol instead. Yep.
I'm not getting ahead, but how do you reference a single bit as opposed to a byte?
You cannot. So this portion of the lecture only explains the lower level logic that the processor uses, but in software you have no control over it. But it is necessary to talk about this so that later on we can refer to the add and the subtraction operations, and then we can then understand how do we have the carry bit from a addition operation or the subtraction operation. So this is still kind of necessary for that purpose. Negation, on the other hand, is represented by overbar. So the negation of x, which is a bit, is x with a bar on top of it. This is the same notation for those of you who want to get into electrical engineering or electronic engineering. This is the notation that they use in those classes. Okay, they're not traditional math notations, but they are notations mostly for gate logic. Okay, the next slide here, this is why I have to open up 2 windows, is because I need this and also this one here. I have to display these 2 side by side because they are related. Now if you look at 0 plus 0 has no carry, 0 plus 1 has no carry, 1 plus 0 has no carry, 1 plus 1 is the only case with a carry. Don't you think that if I want to make a function, to take x and y as input and calculate when x plus y will give me a carry, that carry function will just be an AND. When x is 1 and y is 1, then we have a carry. But for all other cases, for all the other 3 cases, we do not have a carry. Is that making any sense? Okay. So that's why I define the carry of x plus y is xy. The carry bit of adding x to y is x and y. Because the only time adding x to y will give us an actual carry of 1 is when x is 1 and y is 1. The other way to look at this, which is not what I have displayed here, is this is the only case where the result is a 0, but we have a carry to the next digit. This part here is referring to the result. So if we want to express the result, what are the rules? Well, the rules are here. The result is over here. Okay, the result is here. So 0 plus 0 has a result of 0. 0 plus 1 has a result of 1. 1 plus 0 has a result of 1. 1 plus 1 has a result of 0. Is that okay? So we are now only focusing on the result, but not the carry. The carry is done. Okay. So the question is, how can I define, the R function? In other words, if I give you the 2 bits to add, how can you compute the actual result of the addition? Well, it looks like only when the 2 bits are different, we will get a result of 1. When they are the same, I always get a result of 0. Is that okay? Let me say that again. When I'm adding 2 bits and the 2 bits are exactly the same, I get a result of 0, which are these 2 cases. When the 2 bits are different, one is 1 and the other one is a 0, I don't care which one is 1 and which one is a 0, in both cases I get a 1 as a result. So if I want to define a function R to represent the result of an addition, it becomes just the exclusive OR. R xy is x exclusive OR. Are there any questions? Is that okay so far?
That's the same as saying not equal to each other?
Yes. But we can also express exclusive OR using the disjunction and the conjunction only. So let me change the size of this one so it wraps around it more correctly. Okay, there we go. And this is the other way to express it. And when I highlight it, the overbar goes away. So that's why I cannot highlight it. I can just point it out. Okay, what is xy bar? Xy bar is x and not y. Okay, which means if x is 1, y is 0, then y times then x and not y is going to be 1. Okay. What about the other one? The other one is not x and y. When can not x and y become 1? When x is 0 and y is 1. So together, these two account for the only 2 cases that I need the entire thing to be a 1. The first one takes care of the case when x is 1 and y is 0. It will give me a 1. The second case takes care of the case when x is 0 and y is 1. Okay? But when I use a disjunction, that means if one side is a 1, the whole thing is a 1. In other words, this is just another way to express that. It is the same as exclusive OR, but I do not use exclusive OR because exclusive OR is usually a compound operator anyway, and I just want to reduce everything to AND and OR. Are there any questions about this part? Can everybody relate this slide with this slide here, which is something that we have talked about at pretty much the beginning of the entire course? can you relate this part here to this part here? Yep.
Can you just clarify again, you're talking about the x, not y? You're saying
X, not y. Okay.
You're down the bottom. And you
This part.
used the example like if x was 0 and y was 1, you're doing x and,
Okay.
or 0 and.
One way to do it is just to do it by using a table. So you say x, y bar, and then you have x bar y, and there's a plus, right? So what you need to do is to say, okay, what if x is 0, 0, 1, 1, and y is 0, 1, 0, 1? Because this spells out all the possible cases as input to the function. Because each variable is only a Boolean, can either be a 0 or 1, so that's why I can spell out all cases like this. So when you plug in x being 0 and y is 0 into here, then x is 0 will make this term 0. Y being 0 makes this term being 0. 0 or 0 is a 0. Right?
So plus is more.
Yeah, the plus is or in logic gate expressions. We are overloading the operator for that purpose. So in this case, when x is 0, then we don't have to worry about this term because it's going to be 0 anyway. But in this case, when x is 0, x bar is 1, and y is also 1. 1 and 1 is 1. So we have 0 or 1, so the entire term is a 1. Is that okay? And you can work out the other terms too. It becomes exactly the pattern that we want. Is that okay? In other words, on this side, on the right-hand side, we are defining terms used in terms of arithmetic reasoning. 0 plus 0 is 0. 1 plus 1 is a 0 with a carry because we are working with binary numbers. But nonetheless, we are looking at things from the arithmetic point of view. On the left-hand side here, we are looking at the results that we want in terms of arithmetic results, but we are asking the question, how can we do this using just logic gates? How can we do it with and, or, and not? And that's how we come up with these equations. X and y will give us the carry flag, and then x y bar plus x bar y will give us the result. Is that okay so far? The next slide talks about, when it loads, okay, it talks about half adding and full adding. Okay, it's because the equations that we have so far will only give us 1/2 of adding a bit, and this is because we have to add the carry bit from the previous digit also. Okay, and that's why, when you want to look at one single column in terms of addition, there are actually 2 additions involved. Now, we talked about this already, at the beginning of the semester, but it doesn't hurt to go over this again. So to do this, let's see, we don't need that anymore. And we can use, where's my other one? There's no other one. I guess I can use VI for that. Okay, let's go through a simple example. Let's go through a 2-bit by 2-bit addition. We'll just be adding 0, 1 plus 1, 1 as base 2. Okay. Now remember what we did last time? We basically have one row only for the carry bits. This row here is only for the carry bits, and we put a 0 here. Can anyone remind me why we have a 0 lined up with the least significant bit of the addition? Exactly, because there's nothing to give it a carry of 1, so it's always a constant, which is a 0. Okay. So the way it goes is we have to apply the addition once here. In other words, we have to add the input numbers, the input bit patterns. We have to add this 1 to this 1 here, and then that will give us a result of what?
0.
The result is 0, but the carry is
1.
exactly. Okay. then we have a second addition going on because we have to add this 0 to this 0 to give us the final result of this bit here, which is 0. Can you guys see now why we have 2 additions per column? And that's why each addition, as defined a little bit earlier, the C function and the R function, each one is only called a component of a half adder. This one single column here is called a full adder. Okay? We'll just do one more exercise, okay? So in this case, we have 0 plus 1. What is the result of 0 plus 1? It's a 1 with no carry, right? What about 1 plus 1?
0.
Is a 0 with a carry. Now since we only have a 2-bit input, we can expect we can only have a 2-bit output. So that's why 0, 1 plus 1, 1 as a binary number has an output or result of 0, 0 with a final carry. But there's no place to put this carry because we assume the input bit pattern has the same width as the output bit pattern. Okay? Are we doing okay so far? Yep.
So is the C function dependent on the R function?
The
Like
C
define-
function?
I mean, when you had the CXY and
Okay.
RXY, they are dependent between each other because the final results here is depending on the second addition.
Yes. So that's why we have, this slide here. This slide looks a lot more complicated than the other one because according to this, okay, now I can just make a 2 by 2 addition, but this time instead of using, using concrete numbers, I can just name the bits A, B, C, D. Okay. So this time I just say, the first number is represented by bit A and bit B. The second number is represented by bit C and bit D. Is that okay so far? And the question is, how do I express, bit E, bit F? How do I express bit G? This one is always a 0, so I don't need a variable for that position. Okay. And how do I express the final carry? Oh, I should make this G, H, and then this is bit I, and that's bit J. Okay. Okay, so does anyone want to start with this? Well, the easiest one is which one? F is easy, right? What is F? F is R, the result of B and D. Is that okay? What about J? J is easy. J is just F. Okay, because it is a special case, it is the least significant bit of the entire word. So that makes it easy. What about E? E is the result of adding A and C, so that's easy. What about H? H is the carry of adding B to D. Is that right? Is there another way I can get this carry to be a 1? No, there's no other way. There's no other way because the adding of F to 0 can never give me a carry. So that's why I can do this quote-unquote simplification. But I don't have such luck when I get to the bit G, okay? What about bit I? Bit I is the result of adding bit E and bit H. Okay, now how about G? G is the tricky one. Because there are 2 ways for me to have a carry of 1. The carry of 1 can come from, I'm trying to make this so that it is, when people watch the video clip, it will be self-sufficient. When I add A to C, that can give me a carry already, right? If I add 1, 0, 1, 0, then I have a carry. So that means one way to contribute a 1 to bit G is from AC, the carry of A plus C. Okay, so we will say, okay, one way is the carry of adding bit A to bit C. But there's another way, isn't there? When I add bit E and bit H, that can also generate a carry to bit G. So that's why bit G is the disjunction of these 2 carry bits. Like that. Yep.
Do you ever have a case where you have carries in both?
when you have carries of both.
If both-
You cannot.
both of them
It is
are
not
equal.
possible.
Okay.
First one
Yeah.
carries to 0 plus 1.
Okay.
Exactly, but you can definitely the one, a carry of 1 can come from adding the original bits, or the result of adding the original bits and the carry from the previous one. So is this part okay? Does everybody understand what we have from here to here? Is that okay? It's basically exactly the same thing in this slide here, except instead of using bit A, B, C, D, which is actually more confusing, I use X subscript 1 and X subscript 0. X is one input, Y is the other input. The subscript indicates which bit location I'm referring to. Okay? So in this case, if I look at my equation here, and I look at this slide here, I can just basically say the number X has the bit pattern of AB. So X0 is B, X1 is A. The number Y is our CD. In other words, Y subscript 0 is bit D, and Y subscript 1 is bit C. So basically, I just changed the way I refer to the symbols because it is a whole lot easier to type ABCD using a plain text editor than to type all the subscripts. But when I have a typesetting software to help me, I can type all the subscripts that I need in order to give you a more general representation of how things are related. Are we okay so far? Okay. Now, but this does get complicated really quickly, because when you look at bit 3, bit 2, if this is not a 2-bit by 2-bit addition, it's a 3-bit by 3-bit addition, then the carry bit gets complicated. Okay, it becomes like this. And it gets worse and worse as it goes on. So that means if you don't want to use the cascading method, and instead you want to get the result of addition as quickly as possible, the equation gets complicated really, really fast, to the point that you cannot keep track of everything by hand. Okay? Because one way to do it, which is something that we talked about already last time, one way to do it is to have a half adder and a half adder. So each full bit addition has 2 half adders, and it will generate 1 single bit to the next digit. The next digit will do the same thing. It has 2 half adders, and then it will generate a carry to the next one, and so on. But this method is very nice in a way because it is easy to understand. The bad thing about this method here is it needs a long time to cascade or propagate a signal from the least significant bit all the way to the most significant bit. And that's why, in terms of making things faster, people do it like this. Okay? Now look at this equation here. Okay, I'm just going to highlight it. Okay. The lowercase s means the sum. Okay, in other words, this is the final result of adding a number. In other words, it is equivalent to. Okay. It is equivalent to I and j. Okay, that's what the sum bit is. So if you imagine that we have another digit here to the left of I, that would be S2. In other words, J is S0, I is S1, and the blinky cursor here will be S2. If I want a way to calculate S2, this would be the equation to do it. Well, we can do it, right? Because we know what C is. Cxy is x times y, or x and y. We know what R is. Rxy is x y bar plus y x bar y. So if you expand this entire thing, you get the equation to calculate the sum of bit 2. But it will involve x1, x2, x0, it will involve x0, y0. It will involve x1, y1. It will involve x2, y2. But the nice thing about this equation, even though it's really ugly, is it will minimize the propagation delay. Because you don't have to finish up adding bit 0, and then you have to finish up adding bit 1, then you have to add bit 2, then you can get the sum of bit 2. If you do it this way, then the cascade takes a long time. It takes a long time to propagate the signal all the way to S2. If you do it like this, which is a combinatorial way to do it, this will be a lot faster because it specifies the minimum number of gate propagation to get to the sum of bit 2. Does anyone want to expand this using the and the or and the not? How about with a 32-bit processor, we have all the way up to S31, right? S subscript 31. So S subscript 31 will depend on, guess what? X0 all the way up to X31, Y0 all the way up to Y31 in a big, huge, long expression. Do we know how to make that equation? Yes. Do you want to expand it by hand? Probably no. Do you want to lay out the gates on the Intel processor? Probably no. Okay? But this gives you an idea of how to do it systematically. So are there any questions about this? Yep.
So the equation, the R equation, the R, right?
We only have two functions. One is R and one is C. This is a combination of the two. In other words, you apply the R function to x2, y2, you apply the C function to x1, y1, and then when you have these two available, you apply the whole thing to R. Actually, I take it back. I think I got the parentheses messed up somewhere. Yeah, the parentheses all messed up somewhere. But these are all nested. Okay. Are we doing okay so far? Okay. I think there's a closed parentheses to be here. Yep, I think that's the one that's missing. And the open, that should be here. Are there any questions so far? No questions? Oh, nice. I have a little picture here. Yep.
Can you explain K in the paragraph above that?
The K?
Yeah.
Okay. Pictorial, each box is a half adder. Okay. The symbol labeled K1 and K2 are OR gates. This is a K. Okay. Let me just make it a little bit bigger. This is K1, this is K2. These two are OR gates. See, this is an OR gate here, and this is an OR gate here. Is that okay? The OR gate represents the OR to generate the carry bit to the next digit.
Okay.
So this is a pictorial representation, but using the half adder blocks, at the same time. Are we doing okay so far with this? Okay. The next slide talks about the last carry flag, which in this case, in our example, is our G. What are we going to do with it? Okay, that's the question. Because the problem is, if I have 2-bit inputs, I can only assume the output can only store 2 bits. If I have a 32-bit input, I can only expect the output to only store 32 bits. So what happened to this last carry that can be a 1? That's the question. I cannot just throw it away. So what it does is the processor has a special place to put the last or the most significant carry flag. It is just called the carry flag from the processor's perspective. Okay? It is useful for many, many, many purposes. One thing that it is useful for is to indicate when the result of a calculation can no longer be stored in the same number of bits. You have just overflown an unsigned integer addition. Oh, did I just say unsigned? What about signed? As it turns out, you cannot use a carry flag to indicate the result of a signed addition. You cannot use the C flag to see whether you have exceeded what a number can represent using the carry flag alone. So we'll talk about all those flags a little bit later. But this slide just talks about the last carry flag being stored somewhere. It is not lost. It is just being stored somewhere else, but it cannot be stored as a part of the output itself. Now the question now is, how do we know a number is 0? In other words, right after we perform an addition, okay? Just imagine that this is the result after a full addition. The question is, how do I know the result is 0? Well, in terms of arithmetic, you have the equality symbol and say sum equals to 0, and that's to check whether it is 0 or not. That's arithmetic operation. But as much as we like arithmetic operations, we need to translate everything to a gate logic level when we talk about the processor. Because everything inside the processor are binary gates. So the way to translate that in this case is we have a 0 flag. Okay, a 0 flag is 1 if and only if the result of an addition is 0. Are we doing okay so far? Yep.
Why do we ever care if our addition adds up to 0 unless we're actually testing for 0? And then why would we?
Because sometimes it is not addition, sometimes it's subtraction, and subtraction are useful. But let's just say that we only want to see if the summation of two numbers is 0 or not. This will all. Can everybody see that this is all doable in logic gates? The plus symbol, remember, is which logic gate? It's an OR, and then the big over bar on top of everything is a NOT. So this becomes S0 or S1 or S2 or S3 or all the way up to Sn minus 1. N is 32 for a 32 processor. And then you take the disjunction of everything and then you say negate it. Okay? Well, let's see if this works or not. Let's say it is a 0. So that means S0 all the way up to Sn minus 1, they're all zeros. What do you get when you OR a bunch of zeros? 0. You get 0 back. What do you do? What do you get when you negate a 0? You get a 1. So the 0 flag, Z here, which is the 0 flag, the Z flag is a 1 if and only if the number is a 0. I know it sounds kind of counterintuitive. Is it okay? Or is it not counterintuitive? The 0 flag is asserted. How about that? It's asserted if and only if the result is 0. It's an indicator. Okay, it's a flag. You wave a flag when the answer is 0. You don't wave the flag if the answer is not 0. Is that okay? Okay. So we are done with section 3 of this module already. And the next part talks about signed numbers. We won't have enough time today to talk about signed numbers. So you have to read it before Thursday, because we'll continue to talk about this on Thursday. However, it is important to remember, even though in C we have signed and we have unsigned integers, what about in assembly program? There's no such thing. Do you think we have a special addition for signed and one special addition for unsigned? As it turns out, they work. The gate logic that we specify works regardless. And that has to do with how we represent negative values. Okay? The way we represent negative values is called a 2's complement. Okay? So you got to read this part here. Read all the way, read the entire section 4, and also, well, just read the rest of this module here because it is all important. Okay? But particularly, make sure you understand the definition of these flags, because that will come back later on and they are extremely, extremely important. I will be at the lab later today in case people have questions.